All right, welcome to our first notes for Unit 2. Go ahead and take this moment, if you haven't already, to update your table of contents. We're going to be talking about Unit 2.1 today. This whole unit is going to be on linear functions, and 2.1 is all about properties of linear functions. So we're going to start off by talking about things that all linear functions have in common, no matter what. So no matter what the story is, no matter what the context is, every single linear function is going to have these following things in common. So the first thing is that every single linear function will always cross the y-axis. Every single linear function always crosses the y-axis. I'm going to try to improve my handwriting over here. I'm sorry. Okay. So it will always cross the y-axis one time. And when it hits the y-axis, that's what we call the y-intercept. So that's the point where a line crosses or touches that y-axis. That's the y-intercept. And every linear function is going to do that. Another thing is that all linear functions have a constant gradient. Now remember, gradient means the same thing as slope, which means the same thing as rate of change. So all linear functions have a constant slope. They all have a constant rate of change. And what that means is that it's going to be at the same angle the entire time we have this function. So if our function's going uphill, it's always going to be going uphill with the same steepness, at the same rate, the same rise over run the entire time. It's never going to change direction. It's never going to go uphill less quickly or more quickly. It's always going to be a constant rate. And another thing that all linear functions are going to have in common is that all linear functions are either going to be what we're going to call an increasing function, a decreasing function, or neither. And they're going to be one of these categories the entire time. So we're never going to have a function that changes from increasing to decreasing or from decreasing to increasing. If our linear function starts out increasing, it will continue to stay increasing the entire time. So I'm going to do some very quick sketches of what these look like, just because I know it can be confusing just to see the words without seeing a picture to identify it with. So let's go ahead and start by looking at an increasing function. So I drew a very rough sketch of a coordinate plane. So I've got an x-axis and a y-axis. And an increasing function is going to be one where the y values increase. They get larger as we move across our graph from left to right. So if we think about slope dude, as we move from left to right, slope dude will be increasing in height. So as we move from left to right, our y values are getting larger and larger and larger. So this is a function with a positive slope. So slope dude would be moving along this line from left to right, climbing this hill, and it would be a lot of hard work, and he'd be huffing and puffing, and he'd be saying puff, puff, positive the entire time, and he's never going to change. It's going to be hard work forever because this line is always going to be going uphill. So when we think about the fact that this is increasing, we can think about slope dude's position as he moves along this line. His height is always going to be increasing, going uphill. So if we talk about a decreasing function, I'm sure you can guess what this one's going to look like. A decreasing function is just the opposite. If we have a decreasing function, as we move along our graph from left to right, our y values, our outputs, are going to be getting smaller the entire time. So as we move from left to right, our y values are getting smaller. They are going downhill. So as slope dude is going down a decreasing function, he's going to be saying nice, negative, that whole time. That slope is going to be a negative number the entire time. So his position is going to be decreasing in height. So the outputs are decreasing. So I'd like you to go ahead and take a second and see if you can try and sketch what you think a function would look like if it was neither increasing nor decreasing. So go ahead and take just a second, pause the video, and in your notes as you're sketching these functions, go ahead and sketch what you think a function would look like if it was neither increasing nor decreasing, and then come on back and we'll see if you're correct. Okay, so if you took a second and tried to sketch a function that was neither increasing nor decreasing, I'm trying to fix my handwriting and it's not working, that says neither. If you're trying to sketch something that's neither increasing nor decreasing, that is going to be represented by a horizontal line. So as we move from left all the way to the right, we are going to have no rise as we run across this graph. So we are going to be going horizontal the entire time. That is neither increasing nor decreasing. So slope dude wouldn't be going uphill or downhill. He's going straight across. And he would be saying that he's having zero fun because that's a line with a zero slope, zero rise over its run. So that is neither increasing nor decreasing, and that linear function would never change direction. So this would be very boring for slope dude because he would not be going uphill, he would never be going downhill, he would be going straight across the entire time forever. Now you may be asking yourself, wait a second, Mrs. Purvis, when we were talking about slope dude, there was one more type of slope that we talked about, and it was the one that was straight up and down. It went straight up and down, and that was the one that had an undefined slope. And that is true. That is a type of line that we can look at. But a straight up and down slope, if a line has a straight up and down slope, that is an undefined slope. And if we have an undefined slope, that is actually not a function, because it doesn't pass the vertical line test. If I drew a vertical line on top of that vertical line, it wouldn't just overlap in more than one spot, it would actually overlap at every single spot, and it would fail the vertical line test spectacularly. So that line is not a function, and in this unit we are actually only concerned with linear functions, so we're not going to be looking at undefined equations in this unit. So even though that is an undefined slope, that's not going to be one of the three that we're concerned with because it's not a function. Let's go ahead and take a peek at some key features of these linear functions. Some of these key features will be familiar to you because we've talked about key features recently. Some of them are things we haven't discussed before. So let's go ahead and start with something familiar. Let's start with an x-intercept. An x-intercept happens when our line crosses the x-axis. Now, not every linear function will cross the x-axis. The one that will never cross the x-axis is the one that goes straight across. And if it's not going straight across at the x-axis, that means that it's never going to reach it because it's going to keep going horizontally forever. So those are the only linear functions that won't have an x-intercept. But if it has any sort of slope to it, if it has a positive slope or a negative slope, any slope that isn't zero, it will eventually cross the x-axis. So most of our linear functions will have an x-intercept. And that intercept is always going to happen when our x value is some number and our y value is the number 0. So this 0 comes from the y value 0. So that's right here where y equals 0. That's where our x-axis exists. So that is always going to be part of the coordinate pair for our x-intercept. And in this function that we have drawn on the right, this positive increasing line over here, it has a x-intercept right here where it crosses the x-axis, and that is the number -1. So our function is going to have an x-intercept at the number -1, 0. So it crosses the x-axis at the number -1, and that's when the y value is 0. If we're looking for a y-intercept, that's going to be something similar, except we know that every single linear function will always cross the y-axis. So this y-intercept is one that every linear function is going to have. And then y-intercept happens when the x value is 0 and the y value is some number. So wherever it crosses the y-axis, and the y-axis always happens when x is 0. So that's always going to happen right here on this line. So in this case, if x is 0, we're going to hit the line, we're going to hit that y-axis right over here at y equals 1. So we're going to have 0, comma 1, and that's going to be the coordinate pair for our y-intercept. So we're able to find those two key features. Now the slope is something we're also familiar with. And remember, slope is our gradient, that's our rate of change, so that's going to be found by doing rise over run. So if I start over here, I might as well, I already have a coordinate pair. So if I start over here at my x-intercept and rise, I can go up 1 and over 1 and end up right back at my graph. So if I'm looking at rise over run, I can rise by 1 and run by 1 to get my slope. And if I divide 1 by 1, I get the number 1. So my slope is actually the number 1 here. And it doesn't matter where on my function I go, I'm always going to be able to go up 1 over 1. That's what we mean by a constant gradient, a constant rate of change. I can go up 1 and over 1, and I'm always going to be able to get back to my function. Up 1 and over 1, and I'll get back to my function. Even if I decide to rise more than that, I will still get back to my function. Let's say I'm over here and I decide to rise 2. If I rise 2, I have to run 2 to get back to my function, and if I do that rise divided by that run, 2 divided by 2, I still get 1 as a slope. Okay? So my slope is the number 1 here. And let's go ahead and take a look at increasing or decreasing. This is the one that we just learned about on the other page. So increasing means as I move from left to right along my graph, I have to figure out, are my y values getting bigger? Are they increasing, or are they getting smaller? Are they decreasing? So as I move from left to right along my graph, as my x values are getting larger, my y values are also increasing. My y values are getting bigger. So if I was slope dude going along this function, I would always be moving higher and higher and higher. So this function is increasing. And the way that we can tell this is going to be increasing is because its slope is puff positive. So because this slope is a positive one, that means my function is increasing the entire time. So something we haven't talked about yet is end behavior. End behavior literally means what happens at the ends of my function. Oops, I'm sorry. Here we go. Got overexcited. So what happens at the ends of my function? So the ends of my function means as I approach negative infinity on my x-axis, and as I approach positive infinity on my x-axis, as I move toward both ends, what's going to be happening? So we're going to look at x approaching negative infinity. We'll use an arrow to show that we're approaching negative infinity, because remember, we can never get there, but we can get as close as we can. And we're going to be looking at x approaching positive infinity, and we're going to see what our function does. And we can look at what our function does by looking at the outputs of our function. And remember, our outputs are our y values. So let's start by talking about what happens when x approaches negative infinity. So as x approaches negative infinity, we're going to be moving to the left on our x-axis. I want to see what my function is doing, what my outputs are doing. So as I move left on my x-axis, my function is getting smaller. It's going down, which means my y values are also going to be approaching negative infinity. So as I move to the left end of my function, what happens is that my y values get smaller. They're going to approach negative infinity. Now we can do the same thing looking at x approaching positive infinity. So on the right side of my function, as my x values get larger, I'm going to look at the behavior of my graph this direction. My graph is going to be getting bigger. As my x values get larger, my y values are also getting larger. So as my x approaches infinity, my y values are also going to be approaching infinity. So this is what we call end behavior. What is it doing at the ends of our function, at our x-axis? Okay? All right. So this is how we can find the key features using a graph, but we may not always have a graph. So let's go ahead and look at what happens when we just have an equation. Here I have just an equation, f of x equals 2x plus 5. And I want to see if I can find the same key features using just this equation instead of drawing a picture. And it is possible. I just have to use those same ideas that I had in the last slide. So in the last slide we said our x-intercept is always going to happen at some number, some x value, and our y value has to be the number 0, because that's where our x-axis happens, and our x-intercept happens when we hit that x-axis. So our y value has to be the number 0. Now, we only have an equation, and our y value is the same as our output. So what's going on here is this entire output has to be the number 0 if we're going to be able to find our x-intercept. So what we can do to find this x-intercept is go ahead and take the number 0 and set our equation equal to that so that we can find out what x value is going to give us a 0 for our y value. So we're going to take this equation 2x plus 5 and set it equal to 0, and let's go ahead and solve for x and see what we get as an x value. So the first thing I have to do to solve for x is go ahead and subtract 5 from both sides. So we're going to subtract 5 here and subtract 5 here, which means I'm going to have the number 2x equal to negative 5. And the last thing I'm going to have to do to get x by itself is divide both sides by 2. Over 2, over 2, that's a 2. And that's going to lead us to x equals negative 5 over 2. And I do prefer leaving numbers as fractions. However, if you wanted to plot this on an x-axis, it would be easier to know what negative 5 over 2 means as a decimal, so you can find its position between two whole numbers. So we can go ahead and simplify this one step further. X equals negative 5 divided by 2, which is 2.5, so 2.5. So x is negative 2.5. So if I wanted to write that back in my coordinate pair, my x value is now negative 2.5, negative 2.5, and my y value is still that number 0. That was what I get out when I plug in negative 2.5 for x. So that's how we find that x-intercept. Now finding the y-intercept is a little bit nicer actually. For my y-intercept, we have to have 0 for my x value, and then we get some number out for my y value. Remember, 0 for my x value means that I'm on the y-axis, and that's what I'm looking for here. So in order to find the y-intercept using my equation, in this case, what I actually have to do is take this 0, which is an x value, and plug it in my equation everywhere I see the letter x. So I'm going to go ahead and take my function f of x and see what happens when I take the number 0 and I plug it in for x. So that's going to be 2 times 0, and we're going to have to add 5 at the end, which is going to give us 2 times 0 is just 0, and when we add 5, we get the number 5. So my y value is going to be 5 when x is 0. So if I put that in a coordinate pair, my x value is 0, my y value is 5, and I've got my y-intercept. Now, what you may remember, and what it's going to be very helpful to remember as we move forward, is that this equation up here, f of x is 2x plus 5, is in the same form as the equation y equals mx plus b. And the reason this is so helpful is because mx plus b is slope-intercept form. So m means slope, and b, this b at the end, means y-intercept. So if we take a look, this plus b is our y-intercept, which means this plus 5 is our y-intercept, and that's exactly what we found when we plugged it into the equation and got our y value of our coordinate pair. We found the number 5 for our y-intercept. So if we just understand the form that the equation is given to us, we don't actually have to do the math for the y-intercept because they gave it to us in the problem. Now likewise, we don't have to do any math for the slope in this case. I could use my two coordinate pairs and use the rate of change formula, f of b minus f of a over b minus a, but that is way too much work because if we understand the form of this equation, y equals mx plus b, m is the slope. So if I look up in my equation, f of x is 2x plus 5, that number 2 being multiplied by x is my slope, and that's all the work I have to do. There's no other math involved. I just have to be able to recognize that the number times x is the slope of my function. Now the next question is about increasing and decreasing. And remember, we can figure out increasing and decreasing based on the slope. If slope dude would be going uphill the whole time, if he would be saying puff puff positive, if we have a positive slope, that means that we are increasing the whole time. If slope dude would be saying nice negative and we had a negative downhill slope the whole time, that would mean that we are decreasing. And then if slope dude would be having zero fun, that's when we can say that we are neither increasing nor decreasing. So in this case, our slope is the number 2, which is a positive number, which means our line is going to be going uphill the entire time. So if I can find the sign of my slope, I can figure out if it's increasing or decreasing. Now, I know that my function's increasing. If I want to figure out my end behavior, it's actually easiest just to do a very simple sketch of an increasing function. It doesn't even have to be the same increasing function that we've got going on here, so I don't even have to graph 2x plus 5. All I have to do to find out my end behavior is just take a look at an axis, draw a line going uphill, and then figure out what's happening as I approach negative infinity and positive infinity on my x-axes. So as x approaches negative infinity, which means I'm going this direction on my x-axis, my function is going downhill. It's getting smaller and smaller and smaller, which means my y values are approaching negative infinity as well. And this is always going to be the case for an increasing function. If you forget, though, it's really easy to sketch something uphill and see what happens. So as x approaches positive infinity, which is this direction to the right, as we move to the right, our function is going uphill the entire time, which means my y values are always getting bigger. So y is going to be approaching positive infinity. And we have found our end behavior. So the end behavior for a positive increasing function is always going to follow this pattern. And the end behavior for a decreasing function is going to look a little bit different. So sketching a very simple graph of an increasing or decreasing can help you figure out the end behavior. Okay? So in order to get more practice with slopes and intercepts, which are two of the most important key features of linear functions, I'd like you to go ahead and go to Khan Academy and look at the 2 assignments that I've put on there for you guys. There's only 8 questions that you have to answer about slopes and intercepts. I'd like you to have those done by the end of the day. You don't have to write down your work to turn in, but if it's helpful, you can do your problems on a scratch piece of paper. As long as you get your answers submitted in Khan Academy, I'll be able to see that you completed this assignment, okay? Please let me know if you have any questions as you work on this assignment, and I hope you have a good rest of your day.